All right, so I hope you've watched the demonstration links that I posted prior to this video, because I think having the visual is helpful. We find that if we change the magnetic flux through a coil, that we can get current flow. The equation that we relate this to is called Faraday's law. One way to write this is the induced EMF, meaning an induced potential difference or voltage, is equal to the opposite. We'll talk about this for a second. Opposition. N is the number of turns in your coil or loop that you're inducing the voltage in. And then this is the rate of change of the magnetic flux. So the magnetic flux, if it is changed, a voltage will be induced. Now, fundamentally, it's an electric field that is induced. But of course, if we have an electric field, we have a potential difference as well. The two go hand in hand. With this induced EMF or induced voltage, if our coil or loop has a full path, so if the coil itself is looped around and closed, such that there is a full path for electrons to move through, we get induced current. And that's what the meter in the video, the first one about Faraday's law, is representing. You're watching the current flow through the coil. And this is called an induced current. We're getting it because of the change in magnetic flux, not because we have a battery, not because we have the wall outlet power source, but we're getting this current simply because of this flux that is changing. Now, this opposition, technically this part is called Lenz's law. The induced current will always be in a direction to oppose the change in flux. So the induced current opposes the change in flux. If the flux is increasing, then the induced current travels in a direction to try to decrease that flux back down. If the flux was decreasing, the induced current will be in a direction to try to increase it back up. So it's always opposing and fighting, not really fighting, of course, but working to oppose that change. Now, as a reminder, magnetic flux represents the flow of magnetic field lines through an area. The fundamental equation for flux is an integral. If the magnetic field has different values at different locations in the area, then we are required to integrate over the area to find the overall flux. If the magnetic field is uniform in the area, what we mean by this is it has the same value everywhere in the area at the same time. So if you were to look at one single moment in time, the flux would have the same value everywhere in the area. If that is the case, Since this integral for flux is over the area, meaning where, so where a distance, an x, a y, a z, if that field is the same value at every point, we can pull b out of the integral. That leaves us with the dotted with the integral of dA, which is going to give us the area. Now remember, area vector is normal to the plane. The dot product gives us a scalar answer. We can write it in terms of the magnitude of the two vectors times the cosine of the angle between them. So for example, let's say we had an area that everywhere in this area there was something creating a magnetic field pointing into the screen. I'm not particularly concerned about what's creating this field. I'm just saying there is a field everywhere in this area that points into the screen. So if I had some sort of loop, my loop doesn't have to be circular, but this just needs to be a conducting loop. As long as this magnetic field is the same value everywhere in here, we would say the magnetic field was uniform, and so the flux through this conducting loop, in this case right now, would be the magnitude of this magnetic field that's pointing into the screen. I just drew more x's within our loop. I didn't want to draw a whole bunch of x's to fill out that whole region of space. A, the area, would be that area of a length times a width, that rectangular area that I've drawn. So the rectangular area that conducting loop maps out. Right now, theta, the angle between B and A, is 0 degrees. So B is pointing directly into the board or into the screen. A, the area vector, is normal to the surface, which would also be into the screen or out of the screen. In terms of looking at a two-dimensional surface, we typically choose the area vector to be in the same direction as the magnetic field, or at least the component that is. So we'll just say area vectors into the screen as well, and that's why the angle would be 0 degrees. So right now, having this conducting loop in this region, there would be no induced current or EMF even. The reason why is that the flux is not changing. So there is flux. There's totally magnetic flux through that loop. But according to Faraday's law over here on the left, this flux needs to change as time goes on. So it needs to change somehow in order to get an induced voltage. There's multiple ways that can happen. So to change the flux, through this loop, so that we do get an induced current, an induced voltage as well, there are multiple things we can do. We can move our loop left or right, meaning pull it out of this region to the left where it leaves the region that has a magnetic field. If we pull it far enough to the right, it will leave this region with the magnetic field. That's true also if we moved it upwards, it would leave the region with the magnetic field. Or downwards, if we pulled it far enough, it would leave the region where we have this magnetic field. So that is one option of changing the flux. So even though the magnetic field is there, if we pulled our loop down, I just chose down because I have room to draw a picture, part of this loop still has flux, but the portion that is leaving has no flux because there's no magnetic field outside of that region. So in this case, if I pulled the loop downwards out of this region, the flux would decrease. Now, it would only decrease during the time it takes to pull the loop out of the field, but that's okay. During that portion of time where I am pulling it out of the field would be some induced voltage and induced current. So that is one way that we could change flux so that we are inducing a current. Another thing we could do is we could rotate the loop. And by that, I mean, if we have the loop rotated about an axis like this, so that as it turns, we would see a smaller and smaller area. We could also rotate it around an axis this way. As we rotate it, the angle theta between the magnetic field vector that stays pointing into the screen and the area vector, which stays normal or perpendicular to the rectangle, this theta will change. That will affect how much of the magnetic field can actually flow through that area. So that is an option. Another option would be to change the strength or magnitude of the magnetic field somehow. So this magnetic field that I drew pointing in the screen, if we had a way to change how strong it was, that would also change the flux. So there's multiple ways at which we can change the flux. It doesn't matter how we change the flux, but the flux must change. So Faraday's law up here, the flux must change in order to get this induced voltage and induced current. Now in the test notes, you will see Faraday's law this way. The induced voltage, or EMF, we're talking the magnitude, is equal to the number of turns or loops you're going to induce the voltage in, as well as the rate of change of the flux with time. So how that flux is changing as time goes on. Absolute value, just to figure out the magnitude. How big is this EMF? And then in turn, how big is the induced current? Induced current comes because of this induced voltage. If the loop we are working with, inducing the voltage in, has a complete path to follow. So they're taking this opposition part out. It still happens. The induced current still works to oppose the change in flux. That is still the case. But we can calculate values in terms of their magnitudes without worrying about the direction of the induced current. And that is what Faraday's law is getting at here. So we're going to talk both about solving problems using Faraday's law, as well as determining the direction of the induced current. So I'll do those in separate videos, but please, one of the biggest things to keep in mind here is this rate of change, whether we're looking at the original Faraday's law or the one down here. Usually this requires us to take the derivative of the flux equation with respect to time. That's mathematically what that represents. So we will end up needing to write the equation describing how the magnetic flux is changing with time and take the derivative as part of solving for that induced voltage. The other side note that I do see a lot, if you don't think through the math very carefully, we know flux is an integral, and I've had a number of students believe that the derivative over here on the left cancels that integral. But that, of course, is not the case, because this is the integral with respect to area. So with respect to where in the area we're talking about. So this is going to be, the magnetic field would have to depend upon R or X or Y, some sort of distance measurement. Whereas we come over to Faraday's law here on the left, and this is the derivative with respect to time, which of course is not the same variable as area. So that derivative never cancels out the integral. So we have to think through how the magnetic flux is changing to know whether or not we need to integrate versus only differentiate. And we'll go through a couple examples so you can see that as well.